Hi everyone, my name is Thomas Kim. Today is July 4th, 2022. This is my 20th episode for C++ 17 2023 CUDA SYCL OpenGL OpenCL TBB. This is also 5th episode for TBB Internals. In this episode, I will discuss TBB task continuation, also bypassing scheduler. Actually, I already filmed this video in my Korean channel, all in Korean. But for those people who do not understand Korean, I would film this video in English. Also, please understand that I have filmed over 1000 videos. So, if you come across some features that you are not familiar in C++ language, you can search YouTube videos. For example, if you are unfamiliar with placement new Thomas Kim search, then in this video, I explain how to use placement new operator. I will post this script in the description below this video. So by clicking this link or this link, you can learn how to use placement new operator, because we are using placement new operator to create Intel TBB tasks. Also, I would like to recommend this video, Conventional Multithreading, Modern Task-Oriented Programming, Task Stealing Scheduler. If you do not understand what is Task Stealing Scheduler, please double-click this link. By watching this video, you can have better understanding how Intel TBB Task Stealing Scheduler works. Please understand that we have a textbook for Intel TBB 2020. If you click this link, you can download this PDF book. In this PDF book, I will cover Chapter 10, Low-Level Task Interface, Part 2, Task Continuation, also bypassing scheduler. After Chapter 10, I would go back to Chapter 1, Chapter 2, especially Chapter 3, Chapter 4 in sequential order. I would cover this book up to Chapter 19, Progress on Steroid, OpenCL load. Now scroll down from episode 19. Please double-click this link. This session continues from our previous episode. We will restart with Intel TBB task blocking. Then we will proceed to task continuation. Click Show More from Chapter 19, I forgot to upload the source code. I just uploaded. Click this link again. Then you should be able to download the source code. If I miss uploading the source file, please let me know through comment. Unzip it, rename it 020 task continuation. Copy the folder, copy, paste it in your working directory. Now start Visual Studio Code. From folder 20, I would rename it Continuation. Double-click it. Ctrl B. If you haven't watched my previous video, you can watch it now. Here, I would put NL. I would remove these comments. Now, I deleted all, just leaving these things. We will review what we learned in our previous episode. Int fib int n. If n less than 2, we simply return n, else return fib n minus 1 plus fib n minus 2. We will create a class FIB Fibonacci task colon public TBB task. Don't miss semicolon here. I would make it template int cut off. Also template int cut off or parallel fib int n. Void test task blocking int main. We will copy this, paste it here. Now int sum message t message. Scroll up here using message t TBB concurrent vector std string view. Please don't use string view. String view does not work. Use string. Now scroll down here, fib task. We are creating an instance of this class by passing cutoff as template argument for cutoff. It should be L value reference. I would name it root. Now new TBB task allocate root. I would put a line break here. So we are constructing pivot task. Here public int m n int m sum message t L value reference m message. We are creating constructor. Please understand that we have to provide constructor's parameter in the same order. This is the wiser choice. Try to follow the same order. About this, I will discuss in some future session. We have to initialize in the same declaration order m, n, n, m, sum, m, message. This is constructor. So here we are constructing this object by passing n for this n. Then we pass sum. It should be pointer, so we prepend address of operator. Then it should be passed for message. Please understand that we are using reference for message. Don't forget semicolon. Now TBB task spawn root and wait like this, then return sum. So we created parallel pib by creating an instance of pivot task. This pivot task is defined here. Now we need to define execute. This is virtual member declared in task. Right click, go to definition. This class task has a virtual member execute. So we have to implement execute function. Override. This override is optional. Here, if this m n less than cutoff, this cutoff comes from as template parameter. Then this m sum is pointer, so we need to dereference pivot this m n, then return null ptr. Please note that we are calling this sequential function. Now scroll down. Else, in this else block, int x, y, we create an instance like this. It should be L value reference. A, we need to dereference new this allocate child, then pivot task. We have to provide n sum message. Here, this m n minus 1. Please understand that this is n minus 1. If we go up, this is n minus 1. So it is A and it is B in pivot task. So the next comes, we need a sum. This is already pointer. This is already pointer. So this is sum. We pass message. So we can pass this m message. Copy, paste. This is B. Now this is n minus 2. Scroll up. Pivot n minus 2 is task B, this task, I will give line break like this. Now we created two children. A is a child of pivot task, so we used keyword this. B is also a child of this. We need to set this, set reference count. One child, two children plus one for rescheduling. Now this spawn B, this spawn A. We use task schedulers, task stack. Stack is last in, first out, or LIFO. So A is executed prior to B. A is on the top of the task stack. If A is still on the current thread's task stack, A will be executed prior to task B. Now we have to wait until task A and task B complete. So this wait for all. The current thread is recycled to execute either A or B. So our current thread does not just sit idle. The current thread does not sit idle. It is used to execute either A or B or both. After wait, when task A completes and task B completes, then the control should return to this thread. That's why we +1 for rescheduling current task. Here, this M sum dereference x plus y. Here, I made a mistake. This should be x. This should be y. Okay. Now we return null ptr. We will build this program. Before we build, we will call this function by passing 7 as this cutoff value, then 8. It returns result or sum, then print result, and there. Open up CD 020 task continuation CL EHSC SED C++17 continuation.cpp fe m.exe, hit enter. CLS-M. The result is 21. Now we want to test how many threads are used. For example, here talk play fun S stream output pivot task. This MN thread ID. We can use two different ways. I would use standard std this thread get ID NL. Don't forget, it gives nothing. We are inserting this message to buffer. It is not yet displayed on the screen. This M message in place back output.str. We are testing the thread IDs. With this, now scroll down. In this function, we can display this MSG like this. Print MSG, then NL. We are still appending this message to the buffer, but here we display the result. We can use NL for two new line character. We rebuild CLS-M. So we are using one thread. Thread IDs are identical. Now we can change it to 3 or 20. We can try again. CLS-M. So we are using many different threads to compute Fibonacci sequence. Scroll up. Let me fix my wording here. +1 is for resuming this task after wait. So if we do not increase by 1 after wait, the thread does not resume at this line, because after A completes and B completes, this reference count is decremented twice, so it becomes 0. If we do not +1, then this task is destroyed instead of resuming at this part. So number of children +1. +1 is for resuming this task after wait. Also, here in parallel pip, spawn root and wait, print master thread ID SED this thread get ID NL. So the thread that calls Intel TBB spawn root and wait is the master thread. I will make it shorter. For example, 6, 8. We rebuild CLSM. Our master thread or main thread or application thread. 6.0. Our TBB tasks are executed using master thread. In this case, understand the term master thread. Now, I will copy and paste. I will rename it blocking. Now we close blocking. Also this one, Ctrl B. Up to this point in chapter 10, using tasks to create your own algorithm, we covered task blocking, low-level task interface part 1, task blocking. Now we move on to part 2, task continuation. This is intermediate step. Our final destination is task recycling. I will explain task continuation in this episode. In this course, this is pivot task execute function. The thread that executes this line of code is distracted at this line. The current thread is distracted at this line of code because this wait is blocking operation such that the current thread is rescheduled to execute other tasks. Rescheduling entails context switching, which is not free and is CPU intensive operation. So this is blocking operation, task blocking. We remove this part by introducing task continuation like this. I will copy this part, semicolon. I will rename it pip continue. Also, I will copy this part and paste it here. Int x, y, scroll down. We don't need this. I will remove. Also, I will remove this part. Now scroll up. In the pivot continue or pivot continuation, we create constructor int n, int pointer sum, message t, l value reference, message, colon, m, n, n, m, sum, m, message. This is constructor. Now copy this, paste. Return type is pointer. We are inheriting from task. Go to definition. In this class task, we have to override execute like this. Execute override. Now this M sum. This is pointer, so we have to dereference. This X plus this Y. We return null PTR. Now scroll down. Here pip continuation. C. C stands for continuation. New this allocate continuation. Pip count. This MN. This M sum. This M message. So A becomes the child of C. Here C MN minus 1. C X. C message. Also C allocate child. C Y. C M message. A and B are now children of C. Now C has two children, A and B. So C set reference count 2. Now C has two children. Let's go up. In case of pivot count, once it is executed, it does not need to resume. In this function, it does not need to resume after execution. So we set two children. It should be spawned by C because B is a child of C. Also C spawn A. I would delete. Now we don't need to wait. I will fix like this. When A completes, C's reference count is decreased by 1. When B completes, this reference count is decreased by 1. Then this execute function is called. Now we rebuild. CLS M. The result is 21. If you want to trace this figure here, you can do this. Here, talk play fun, stream, output, pivot, con, this M N X, this X, Y, this Y, and L, this M message, in place back, output str. Now we build again. CLS M. So It works perfectly. Please compare this with this figure. How this is executed with these figures and this result. If you need to, you can add more debugging code here. Now let's consider what does allocate continuation do. Talk play fun, S-stream, output, pivot, task. This MN is parent. This parent NL. I would say before copy this, paste is parent after. This M message output str. So before executing this line of code, pay attention to allocate continuation. Before this line, current pivot tasks parent pointer. After this operation, current pivot tasks this parent pointer. We rebuild 97. It should be in place back. Rebuild CLSM. So pivot task 8 is parent before it has parent. Pivot task 8 after its parent become null. Pivot task 7 is parent before it has parents. Pivot task 7 is parent after it becomes null pointer. This allocate continuation nullifies the current pivot task's parent to null and set the current pivot task's parents to C, the piv count, as its parent, as the parent of the piv con C. Now scroll down. We are spawning B. By spawning, we push B on the top of the thread's local deck. I will pronounce this word deck. Such that the task scheduler can schedule its execution. Instead of doing this, we disable like this. Then return the address of A. We effectively bypassed TBB task scheduler, or bypassing the scheduler. We build once again CLSM. The result is the same. For more information, please read the documentation here. Also, bypassing the scheduler, we commented out this part and modified like this. At this line of code, we effectively bypassed the TBB task scheduler or bypassing the scheduler.